is isn't there a light outside there? So this is the relationship between force on one hand and acceleration on the other. And what we will do is we will sort of compare these two results, and we will try to see whether there is a fundamental difference between the relationship between force and acceleration as seen between the two views, between Newton's view and Einstein's view. First of all, in both the views, force is the rate of change of momentum. So this part is the same no matter whether you are doing Newtonian mechanics or Einsteinian mechanics. Okay. But in Newtonian mechanics, at least for point particles, we are just talking about a single point particle here, only this force that is acting. In Newtonian mechanics, the momentum is simply given by mass times the velocity of the particle. And as always, we are calling the velocity u rather than v, simply to distinguish it from the velocity between states. And this translates simply to a result we all know. Now, one immediate consequence of this form, which is obvious but which is not stressed often enough, is that force and acceleration always occur in the same direction. Right? Force happens to be equal to a scalar, the mass, into a, the acceleration. So force and acceleration are co-directional no matter which direction the force is in. Right? That's something which is very trivial and follows obviously from this equation. But we will soon see that in the Einsteinian version, that doesn't really work out. Because in the Einsteinian version, what you have is this is rate of change of momentum, of course, but the momentum is no longer given by mass times u, it's given by an additional factor. And because of the additional factor, the differentiation becomes simply this, m gamma u du vector dt, or let's just call that a, you already know that that's the acceleration, plus m d gamma u dt a. I may have departed from my earlier notation where I wrote gamma with u suffix. U, of course. Yeah, that's great actually. Thanks for pointing that out, because that is exactly the important point. Notice that this tells you that the force is a linear combination of two things, two vectors, A multiplied by m gamma u and u multiplied by m d gamma u dt. And what that means is that in general, if this is A and this is u, force would be in some direction like this, right? You multiply A by m gamma u, multiply u by m d gamma u dt, and you get to complete the parallelogram and you get f, right? So f in general is not in the same direction as A. That's one huge difference. Okay? So in relativistic physics, force and acceleration are not necessarily in the same direction. Okay, it follows simply from the calculus, so it's nothing we can do much about. But let's point out that there are two situations. So force, okay, I'll just not write the whole thing, it will take me too long. F is not parallel to A in general. So in stark contrast with what we had in the Newtonian case, force and acceleration may very well be in different directions. Okay. right? Of course, one thing is important. Acceleration here is multiplied by a positive quantity. What that means is the force will always have a component in the direction of the acceleration. Although force and acceleration are not co-directional, it will not happen that the force is in this direction, the acceleration occurs against it. But not necessarily in the same direction. There are two situations where this problem or rather this unusual thing will not occur. There are precisely two situations where force and acceleration will be co-directional. One of them is obvious, which is u and a are in the same direction. So except one possibility is u and a are parallel. Okay, even there are three possibilities. The third one I'm not going to mention, or the third one I'm going to mention right now. The third one is if u is 0, right? Of course, if u is 0, the second term is not there. Force and acceleration will be parallel, but in the presence of an acceleration, u cannot stay 0. If u is 0, it's 0 at an instant, and then it will change. So, and that actually, if u is 0, you can actually say that u and a are parallel, doesn't matter, it's subsumed in this. Well, there's one more case when u and a would be parallel. F and a, sorry, not f and, not u and a. Force and acceleration will be parallel, which is?
U and a are perpendicular. U and a are perpendicular.
Why?
Because d gamma u by, because u dot a would be 0 in that case.
Basically, what you want is d gamma u dt to be 0. Right? If d gamma u dt were 0, then of course only the first term will survive and f and a will be parallelly same, and d gamma u dt being 0 can happen if gamma u is a constant. But that's really the trivial situation where there is no acceleration at all. Gamma u, remember, depends on the speed. Okay. So if a is 0, a is constant, of course there is no acceleration, gamma u is a constant, no problem. The other situation where gamma u can, of course, if speed is a constant, like in a circular orbit, uniform circular orbit, velocity is not unchanging, so you do have an acceleration, but there the u and a are perpendicular. But even more generally, d gamma u dt will vanish where gamma u has reached an extremum, right? Either it's a constant or it's a maximum or a minimum, right? That means u squared, the length squared of the velocity, that has to be an extremum. And that happens only when u and a are perpendicular to each other. Although we know this, right? If you don't, you will see this soon from the math. But velocity extremum, speed extremum, not velocity extremum, speed extremum is reached when velocity and acceleration are perpendicular. Okay? That's easy to show, in fact we will show this very soon. So if you don't happen to know this already, you will just see that soon. But that is the other case. Perpendicular. So these are the two possible cases where force and acceleration turn out to be co-directional. Okay. Well, in the two cases, in these two special cases, one of them is okay. Before we go there, let's just rewrite the d gamma u dt in a form that will make the second statement obvious, and we will also need that form. We have actually seen this several times before. You need to differentiate gamma u, but obviously it's much easier to differentiate this, because that's simply this, right? Rather than deal with a lot of square roots and 1 over square roots and so on, it's easier to just differentiate this. What you get by differentiating this is obviously minus twice gamma u to the power minus 3 d gamma u dt equals minus 1 over c square times ddt of u square. Okay. What is ddt of u square? twice u du dt or twice u vector dot du vector dt. Both of them happen to be the same. Remember, u square is u magnitude square is also u vector dot u vector. And if you differentiate that latter expression, what you are going to get is twice. Okay, and which is why d gamma u dt being 0 translates to, just move the gamma u, the minus u to the other side, this is what you get, right? And d gamma u dt being 0 translates to u being perpendicular to A. Right? Yeah.
I have a question, a different question from related to the leftmost thing on the board. Sir,
That is F.
yes.
Why is it dp dt?
Yes, and why is it not dp term?
Because force doesn't have to be. Okay. That is a very important question, and we are going to perhaps return to it if we have time. But frankly, you don't. P vector, remember, is a 3 vector, right?
Yes.
It's not. P vector is not a 4 vector.
Oh.
Okay. Now you might that is still not a good enough answer, because you might say capital P mu, the 4 vector P, has P vector as a spatial path, and the 4 force should be dp mu d tau, because that will be a 4 vector. So this F dp vector dt is not a spatial path of a 4 vector. It is a 3 vector in its own right, but it's not a the spatial part of 4 vectors are automatically 3 vectors, but this one is not the spatial part of a 4 vector. So you might of course ask, why is it not that we define capital P mu dp mu d tau, which of course would mean d tau of mc m gamma uc m and p vector, right? This is, or p, it's easier to write this as p over c and p vector, right?
Yes.
Well, you could do that. You could define this. In fact, this is actually a useful quantity. And then you should realize that dt tau is of course related to ddt. We have already seen that several times, right? dt tau and ddt, there's an extra gamma u factor which comes in. That's a gamma u factor which came in all these calculations. So you get gamma u by c dv dt and dp vector dt gamma u. The spatial part of this 4 vector k mu is not the force, it's force times gamma u. Now which one should be the force? Should you call force times gamma, what we used to call force, just like what we used to call momentum, m times u. We are seeing now that m times u is not the 3 vector part of a 4 vector. Rather, m gamma u times u vector is. Right? So we decided to multiply the mu vector, the momentum that as we knew it, by an additional gamma u, so that it really becomes the 3 vector part of a 4 vector. So why can't we also do the same thing? Why can't we say force vector has been multiplied by gamma u to give you the actual force vector? So why don't we say this is F, this whole thing? We could have. We don't need to, because we already have expressions for force, right? Like say the Lorentz force law. The question would be QE plus V cross B. Would that be equal to dp vector dt or dp vector dt times gamma? And the answer to that is, if you did the full electrodynamic analysis, it would turn out to be dp vector dt. Okay, that's one way of getting out of it. The other way would be to say, that's just simply experiment. Which one of the two should we call force? Should be decided essentially by experiments. And experiments tell us that this is dp vector dt. If we had done a full electromagnetic theory, relativistic version of that, then I would be able to convince you a bit better that QE plus V cross B is really not the spatial part of a 4 vector. Of course, you could then go and say that why do we have to stick with the Lorentz force law as as we had done before, why don't we say the Lorentz force law, the force should be defined to be that times gamma u. But that is a trivial thing, the gamma u would be just cancelling each other out, not giving any new physics. Remember, in the momentum definition, putting in the gamma u makes a huge difference. As you can see, the force is no longer in general in the same direction as the acceleration. That, of course, is a very new thing. Putting in an additional gamma u in what I call the force, and when I say the Lorentz force, when I ask what is the force acting on a charge when it's moving in a electromagnetic field, you put in an additional gamma u there. The two gamma u's will just cancel each other out. They will not give you anything new. So, we don't change the definition just because we want to change it. We change the definition because changing that would be useful. So, we stick to dp vector dt rather than dp vector deta. Although I take your point, that might be a natural thing to do. But doesn't really give you any additional advantage, so we don't do it. But that's a good question actually. It should have been a natural question to ask. But anyway, coming back to this, we have seen that d gamma u dt is of course something which has a u dot k by c square in it. So plugging that in our expression for force, we get this result. F vector is m gamma u vector plus m gamma u cube u dot a by c square u. Oh, this one is a vector, right? Of course. Yeah. So, now, this is the full expression for force written down in terms of acceleration and e. Okay? Two special cases as we mentioned. Let's do the transverse case first. Transverse is when u is perpendicular to a. Why are these two special cases interesting? Because these are the two cases where force and acceleration are actually perpendicular to each other. Oh, sorry, parallel to each other. Okay. If u is perpendicular to a, this second term is not there, right? Then the force simply works out to be m gamma u a. So instead of mass m, the factor which tells you how little the body accelerates when you have a force is in this case given by m times gamma u. So this m times gamma u of course has the same dimensions as mass and plays the same role as mass in this specific case. And it's the traditional role as a measure of how much inertia a body has. Right? So this is actually called a mass. It's called the transverse mass. Why transverse? Because this is the transverse case where u and a are perpendicular to each other. Okay. It so happens that this transverse mass mt also happens to be equal to something you already know, the mr. Okay. So remember, mr is basically this factor which is fitting in the definition of the momentum. And here we see that the same thing is sitting in this case, right, between force and acceleration, but it's just sort of more of an accident why mt and mr happen to be equal. Mt comes out of m gamma u from this calculation, right? But before we go there, let's look at the longitudinal case, which should make it more obvious why mt being equal to mr is more of an accident. In the longitudinal case, what happens? U and a are parallel to each other, right? So in this formula, u and a are in the same direction. Now what that means is something which should be rather obvious to all of you. You can rewrite this expression as this, right? Same direction, and this is basically u by c squared times the magnitude of a. You are multiplying by u vector, so the overall magnitude is u squared by c squared times the magnitude of a, same direction, right? But this of course works only because u is parallel to a. Otherwise this wouldn't work. Okay? So in the longitudinal case, so when two vectors are parallel to each other, then u dot a is just simply magnitude of u times magnitude of a. Right? This dot product here. Is this clear to everybody? That these two things are the same? And same only in this case, where u and a are parallel. Of course, otherwise, an equation like this simply cannot be correct. This vector is in the direction of u, this vector is in the direction of a. Only when the two are in the same direction will these two results match. But then, in the longitudinal case, now Newton has served this purpose for the time being. So let's move him out of the way. In the longitudinal case, once again let me remind you that longitudinal simply means u and a are parallel, and as a result f is parallel to a in this case as well. What you have is m gamma u a plus m gamma u cubed u dot a by c square u. That thing I am going to replace by u square by c square into a vector. Right? But now notice one thing. If I pull m gamma cube u a out of the whole thing, what do I get? Here I get 1 by gamma u square. Right? Now you might say that's a bad thing to pull out. Why not pull out m gamma u a, which is obviously there in both terms? But you will soon see why. In fact, you know why. 1 by gamma u square is something nice. Yes? And when you pull out the m gamma cube u a from this, so you get m gamma cube u a. So this is once again a situation where force and acceleration are parallel. Force is something times acceleration, and that something will also be called a mass. And this is the so-called longitudinal mass. Okay? And ml happens to be m gamma u cube. So typically way bigger for very fast moving objects than either m or mr or mt. Right? Mt is m gamma u. These are the two measures of inertia in the special cases where force is parallel to the acceleration. Okay? In other cases, basically the effect is a mixture of these two factors. You can always write when say the force, when the acceleration is not in the direction of u or perpendicular direction of u, you can always break it up in two pieces. One in the direction of u, one perpendicular to u. Each individual piece will basically be affected by different factors.
So,
Yeah.
so why are we so concerned with trying to meet the force force in the same direction as acceleration?
We are not.
Because the formula just says that it is not. So
In general, it is not. There are special situations where it is.
why are we so concerned about this?
Well, basically, several reasons. One of them is, two of them. Let me give you two of them right now. These are the two situations where the thing is easiest to do calculations with. Okay, easiest to analyze. And a more important reason is that at least the transverse and the longitudinal case, these are actually special cases which happen very often. Longitudinal case, give a force, suppose you have a particle at rest, applying a force in a given direction. Which way will it accelerate? Along that direction? Which way will it move? Along that direction again? Right? So it will move in one dimension. If it moves in one dimension, then the longitudinal case is exactly what you have. So for one-dimensional motion, what is very important to remember that the mass which relates the force and the acceleration is not the relativistic, not the rest mass, neither the relativistic mass. Okay. In fact, I could have subtitled this, the heading was relationship between force and acceleration. But I could have also subtitled this topic, why I hate relativistic mass. Relativistic mass goes in only one small place. You have all kinds of other masses which play the role in different places. Okay, so you should always realize that the actual invariant mass, which makes sense no matter what physical scenario you're talking about, whether it's a relationship between mass and acceleration, or mass and, say, between force and acceleration, or the momentum and velocity and so on, there's only one mass which really features in the same way in all of them, which is the invariant m. Okay, the other things you have to change depending on the situation. And the most dangerous thing happens to be the other special case where this equation is commonly available, which is when force is perpendicular to velocity. When does that happen? That's a circular motion, and which is the simplest possible situation where you would find a fast moving object moving in a circular path. Charged particle in a magnetic field. In fact, you have seen the experiment, D by M thing. And by the way, I don't think we went that far, but did you also talk about cyclotrons, etc. sometime? Okay, and the reason why the cyclotron works is that the time period it takes for a charge to move actually the constant is independent of how fast it's moving. In a magnetic field, if it moves faster, it moves in a bigger circle, exactly in the same ratio. So the radius and the velocity are always proportional, so they always cancel out. And you get something called the cyclotron time period or the cyclotron frequency, which depends only on the magnetic field. Okay? And that is essential because for the cyclotron to work, the speeding up, a cyclotron is basically used to speed up particles, right? The speeding up cannot happen because of the magnetic force. Magnetic force is no work. It doesn't increase kinetic energy at all. The speed up happens because the cyclotron disk is actually connected to two pieces called Ds, and every time the electron goes from one end to the other, or charged particle goes from one end to the other, the electric field radiation changes. And that's easy to do. All you have to do is give a fixed frequency AC, which reverses every time the electron comes in. But that works only because the frequency is fixed. Now, I just said electron a while ago, and I corrected myself, because an electron is the worst kind of thing you would want to accelerate in a cyclotron. What is typically accelerated in a cyclotron are heavier particles. Particles which typically move much slowly compared to the speed of light. Okay? For those particles, this result that the cyclotron frequency is a constant is right. But once the particle speed approaches that of light, the mass of the particle cannot be used any longer. You have to use the transverse mass, because the motion is transverse. Okay? And the transverse mass grows with speed, which means the cyclotron frequency now no longer a constant. So once the particle speed is much larger compared to, not larger than the speed of light of course, but close to the speed of light, then you can no longer accelerate it effectively using a cyclotron. Okay? You can accelerate effectively using a cyclotron only if speed is less than 1% of speed of light or something. Okay? Which is typically the case for, say, rather energetic protons or alpha particles, but not at all the case for electrons. Okay? Yeah.
You wrote u vector dot a vector by c square u vector. So then you wrote u square a vector by c square. Only when u is parallel to a vector.
Yeah.
So if u is parallel to a vector, then shouldn't the magnitude of a vector? You wrote a vector. Magnitude of a.
Is the left hand side a vector or scalar in this expression?
Is a vector.
Both sides have the same magnitude. You're right about that. But they also have the same direction. Right? U and A are in the same direction. That's why I wrote a vector. That's a vector identity. In the special case, of course, when U and A are parallel. Okay, let's come back to this issue. The issue is, the only issue that I want to make out of it, because this is not a course on cyclotrons, is simply that this failure is attributed to the fact that the mass increases with speed of speed. Okay. Which mass is that? Which mass? Is a transverse mass which increases with speed. Unfortunately, and very unfortunately, this transverse mass happens to be the same as the relativistic mass, which is why this misconception persists in even textbooks, that what is going on there That's not the misconception, that's perfectly right. But the unfortunate misconception which persists is everywhere you want to use force and acceleration, you can just replace the mass with the reducing mass. It just happens to be correct in that one special scenario. It's wrong entirely when the particle is moving in one direction. If a particle is moving in a straight line, you cannot replace the mass by the relativistic mass. It's actually a much larger entity that goes in there. So, basically, my whole point is trying to hide the fact that our formula for momentum has changed by inventing a new kind of mass soon brings us into many different kinds of mass. And also, if you are not very careful, makes you think that you can just replace m by m gamma u everywhere and everything will work. It won't. That's the whole point. Which is why it's always best to keep on remembering that all you have done is realize that the formula for momentum has changed. You did not really need the MR. The MR was just there simply to satisfy a childlike wish of keeping the formula the same. Of course, the other thing, important thing MR is good for is E equal to mc square. That is something which is, nobody will ever get rid of relativistic mass no matter how much they try, because you will not get rid of E equal to mc square from the textbooks. Okay? So, that m, once again let me remind you that m is mr, not n. Okay. Although we write it as m all the time. Okay, now this is one part of the gone. In the second part, I would like to show you that this energy momentum conservation 4 vector that we talked about and its conservation principle can be used to make very important predictions about various physical situations, especially for high velocity situations. In the low velocity situations, things should go back to classical physics, so you don't really need the relativistic formula for that. So typically, situations where you see applications of the relativistic formula better are things which happen in the world of the very small, because those objects tend to travel very fast. So things like nuclear decays, nuclear reactions, a photon going and hitting an electron, that kind of thing, you would really need the relativistic formula for. So let's try to put this to use in analyzing some of these situations. But let me just remind you before that, two things. One is a 4 momentum. Now I will not put a mu on top, I will just assume that when I write capital P, you know it's a 4 momentum that we are talking about. Okay. The reason why I am not going to do that is soon it's going to get very cluttered if you also keep on writing mu. And this is the whole object I am talking about. It's E by C, P vector, and its norm, we will write this as capital P squared, although you should realize this is not really necessarily a square of a real entity. This one is of course positive, but in general it may not be. And this turns out to be equal to m square C square. The long way of seeing this is just use the formula for E, formula for P, and do the calculation. The short way is to realize that this is an invariant, so it is the same in all frames. So in particular in the frame in which the particle is at rest, its rest momentum is, rest mass is mc, rest mass is m, the 4 momentum would be mc, 0, and that of course has a norm of m square c square, and that is the same in all frames. That's an important thing. And one more thing that you will need, a bit of notation. We have already talked about this. For 2 4 vectors, A mu and B mu, this is the invariant, right? You have to make one into a covector, or you multiply the 0 components together and dot these. In keeping with our statement that I don't want to clutter up this thing by writing a mu, I will not have access to this A mu B mu notation soon. So what I will do is write this as A dot B, but instead of dot I will put a tiny square there. Just to remind you, this is being done in 4 dimensions. This is not the same as the, so this is the dot product in 3 dimensions. This is the 4-dimensional deviant dot product. By the way, nobody uses this notation, so you don't go looking for this number. It's just that Okay. Books of course have typefaces. They can use other types to show things. I'm just using a square in between to show this is a 4-dimensional invariant dot that we are calculating. In what sense? Of course, we have different expressions. You cannot even do A dot B for 4 vectors, right? A dot B, the A dot B on the right hand side is for 3 vectors, the 3-vector pass. Are they mathematically different? Is a very difficult question to answer because at one level they are identical. They are both scalars that you get for your respective transformations. A dot B is a scalar under rotations, and this A squared B is a scalar under Lorentz transformations. So in that sense, they are basically the same thing. But mathematically, of course, they are very different as a formula wise. And one interesting result that we will need, and which we will not bother proving because the proof is trivial, you can all do it, because this is the same as the same formula that we had for dot products or just even A plus B whole square. Okay. The only thing is that twice AB factor there is the invariant scalar product between A and B. Okay. Now we have been harping on the word invariant quite often, and you will soon see why this invariance is of great importance in calculations. But before doing that, let me at least point out one situation or one result of great importance which follows directly from energy momentum conservation. Remember, now I am not going to write P any longer, but I will write PS or let's say Pi. This is the initial. Okay. And let's say there are n particles labeled with the index A. This is an energy momentum conservation relation that we wrote down. A running from 1 to n. In the absence of external forces, this is what you are going to get. Pf, B. B will go from 1 to n bar. A and B are just indices which keep track of the particles. It's labeled different particles. Okay, yeah. Both 4 vectors. No. You cannot add a covector to a vector. As simple as that. If you did, you will not get something which is useful. You can of course by force try adding them. Right? You can only add vectors together, you can only add covectors. You add 2 vectors together, you get a vector. You add 2 covectors together, you get a covector. Adding a vector to a covector gives you nothing meaningful. This relationship actually will work irrespective of whether A and B were both vectors or A and B were both covectors. Now this is our energy momentum conservation relation. And so far in all our, yeah.
So why are we writing the invariant norm as P squared?
Why are we?
P square by C square minus P square
Yeah.
is P mu by P lower mu, right?
Right, that's writing that as P square is just a notation for this. This is the equivalent of squaring length of a vector. When you square the length of a vector in 3 dimensions, you do take the 3 components, square them and add them together. Why don't you do it here? You have 4 components. You could have squared them and added them all together. But doing that will not give you an invariant entity. The importance is in the fact that this is an invariant, not in the fact that it's a positive thing or negative thing or whatever.
But we can write that as P square.
We write, that is just notation, right? For a 4 vector, P square is P upper mu, P lower mu by definition. Remember, when you say square of a 4 vector, you will define that thing. What does it really mean? You can of course invent an entirely different notation for this, but you don't need to. There is a standard notation people use. The only danger with this notation is when you square a 4 vector, you may not get a positive number. You get a positive number for time-like situations. Like here, you get a negative number for space-like 4 vectors, you get 0 for null 4 vectors. Now, in all the examples that we have talked about so far, we are really concentrated on the spatial part of these equations. We have looked at momentum conservation, right? So far we have been talking primarily about momentum conservation. But we are also seeing that the moment you write this as a 4-vector relationship, the relationship has to be true not only for the spatial part, but also for the temporal part. So you should also have temporal part conservation, which is just energy conservation. You just ignore the 1 by c which is there on both sides, or rather cancel out the 1 by c from both sides. You simply get this. Take all the initial particles, add their energies together, and all the final particles add their energies together. Remember, n and n bar may very well be different. You get the same result, right? This is just energy conservation. Now, one thing that becomes rather useful here is if you rewrite the fact that the energy of a single particle is actually kinetic energy plus is rest energy, right? So if you write it that way, and I don't put an I or an F here because rest energy is an invariant quantity and it's not also a constant, it doesn't change with time. EBS, okay, having so many EBF summed over B from 1 to n bar. Okay. Now this happens to be one of the most important equations in high energy physics or nuclear physics. This is a very simple equation, but what it really says is the following. The net kinetic energy of a system can increase or decrease if and only if the mass is changing. Okay. If the mass decreases, then the kinetic energy can increase. If the mass increases, the kinetic energy has to decrease. Right? So basically what this is telling you is delta is given, the increase in kinetic energy is given by decrease in mass energy, right? It's given by this quantity. Whatever mass you had before minus whatever mass you have at the end into c square. Now, why is this an interesting equation? Simply, it's really nothing much. It's just that equation written down, right? It's just energy conservation. But why is this important? Because of the fact that everything from the atom bomb to the fact that the alpha particle decay can occur, or the proton cannot decay as far as we know. All of these, or the electron definitely cannot decay as far as modern theory goes. All of these are really something which follows from this. You know, our entire, well, not entire, but at least one of our major sources of energy, in a sense, all our source of energy hinges on this equation because if nothing else, every part of our energy in some way or the other comes from the sun. And sun's energy, of course, comes from this. The fact that when 4 hydrogen atoms ultimately fuse via a rather complicated chain to form helium, the mass actually goes down. And the energy is released, and part of that energy is what we get. Yeah.
Can you repeat what is A and B?
A is an index, B is an index. You have 10 particles to begin with, they are different particles, right? So to label them differently. We are using different indices for beginning and ending, right? Because A and B would typically go over different values. Okay, let me just look at the special example and that will make it obvious. Let's look at this thing. We've all seen this before, right? Alpha decay, what happens? A nucleus X decays to produce a daughter nucleus Y plus an alpha particle. Of course, the mass number goes down by 4, atomic number goes down by 2, and so on from X to Y. But right now we are interested more in the energetics of it. First of all, can this always happen? Let's look at this situation. This is a decay process where only one particle is available at the beginning, right? Only X. So let's look at this from a special frame where life will be easier for us. the frame in which X is at rest. Right? So you have a nucleus, supposedly radioactive nucleus, at rest in your frame. Okay. So what's the energy that you have to begin with? Just mx square, right? Nothing more. Energy conservation would ensure that once this decays into these two particles, you will have this equal to Ey plus E alpha, right? Kinetic energy of the Y particle plus kinetic energy of the alpha particle plus myc square plus m alpha c square, right? So for this decay to occur, if this decay occurs, Ty plus T alpha, the sum total of the kinetic energies of the decay products. In fact, this is exactly this relationship. Initially there was no kinetic energy. What is the final kinetic energy? Ty plus T alpha. So Ty plus T alpha is the increase in kinetic energy. And that's equal from this formula, from this equation rather easily, and also from that equation. For this particular process, A was an index which took only one value, capital X. Right? There was only one particle to begin with. And B was an index which took two possible values, capital Y, or indices don't have to take values which are numbers, right? They are just meant to indicate. So capital A is capital X, ran from only one value, and B ran over two values, capital Y and capital Alpha, and alpha. Okay, so this tells you that the net kinetic energy of the decay products, in this case the alpha particle and the daughter nucleus, is given by this quantity. And this quantity has a special name. This quantity in general, the decreasing mass energy, has a special name. It's called Q in difference to chemistry. Basically, chemists use this all the time for heat of reaction. Right? This is basically the energy available after this decay takes place, after any new reaction takes place. Yeah.
So what kind of mass is here? So what kind of mass is here?
All masses here are masses. So that is why you should not have different kinds of masses. This is mass, end of story. Or if you really want it in the old language, rest mass.
So suppose it's 6 kilo, I mean the mass before and after.
That would be mass conservation, right?
Yes.
Mass conservation, classical physics would insist on mass conservation. Relativistic physics says mass doesn't have to be conserved. Why do you need mass conservation? We needed mass conservation if you look at this from a purely theoretical point of view, because momentum conservation had to be Galilean covariant. That was the case in Newtonian physics. Momentum conservation being Lorentz covariant leads to energy conservation, not mass.
So, but you are saying that is rest mass, right?
Yeah.
So, rest mass has to be conserved.
No, it's not. What has to be conserved is relativistic mass. For the simple reason that there is no such thing as relativistic mass, it's just energy. Energy by c square. Energy being conserved means if you divide it by c square, it will be conserved, right?
So say mass is an example of a quantity that is an invariant but not conserved.
Rest mass, okay, let's be pedantic and call this rest mass. Rest mass is an example of a quantity which is constant, doesn't change with time, invariant, same for all observers, but not conserved in the relativistic scenario. Of course, difference between mx and my plus m alpha is extremely tiny. Okay, it is extremely tiny, which is why before Einstein brought this up, we had lived forever with the idea that mx equals my plus m alpha. It is the fact that the mass number decreases by 4 in an alpha decay is mass conservation, right? But you remember that mass number is not the actual mass of the object. It's an integer closest to the mass. Okay, that being the same before and after is not the same thing as m being the same.
So sir,
Yeah.
this quantity, so like for nuclear energy and stuff, or
Everything comes from this.
so
Not nuclear energy, in fact, even any energy. Suppose when I heat up suppose I have a 1 kg object, I heat it up. It now has more energy. Its mass is actually larger. But larger by how much? Larger. If you heat it up, it has more energy now. So its mass is now larger, but larger by how much? By whatever energy I gave it, by c square. C is such a huge number that this increase in mass in everyday objects is something you can never see. It's way too small to be observed. Whereas increase in mass or decrease in mass in nuclear particles, even that is tiny. It's not as if you get a huge change. But that tiny change produces a huge energy difference because of the fact that you have a c square factor there.
So sir, can I comment that when people write, most of the time when people write equals to c square, they mean this formula actually.
Of course. No, they don't mean this formula.
I mean,
They mean E equal to mRc square.
yes sir, but most of the
Yeah, but a special case of that is when rest energy changes, you get that as kinetic energy. So very of course, a special case of the E equal to mc square formula is E0 equals m0 c square. The rest energy of a particle is, in fact, what you are saying is total energy is the sum of the kinetic energy and the rest energy. And kinetic energy can increase or decrease at the expense of the rest energy, which means at the expense of mass. Okay? Now, well, there will be one more class after this for the simple reason that when I say one more class, I don't mean that not one more class today. Okay. And not one more class in this semester because there are more classes. Well, I mean one more class on relativity after this. I wanted to end today, but of course, ending it here would be rather bad. I want to demonstrate several things. One of them is a very interesting and important result. Okay, let's see. I can do that in 2 minutes in the classical scenario. Okay, does this tell you what the kinetic energy of the alpha particle is? It just gives a sum, right? However, you also know that this is true. How much is this? Py plus P alpha is basically P of x. But in the frame that we are looking at, what is P of x? 0. Because the particle is addressed there. So you have momentum conservation along with energy conservation. Both of them are already available. Energy conservation gave you this. Net kinetic energy of the y particle and the alpha particle is given by this matrix, right? Momentum conservation tells you this. Now I'm going to do something which seems rather nasty, which is, although we have relied entirely on relativistic calculation so far, I'm then going to say that in most alpha decay processes, the alpha particle comes out with non-relativistic speeds which are not close to the speed of light. Okay. Now, how do you judge that? The easy way to judge that would be to look at the energy. If the energy is close to the rest energy or more than that, when I say energy, I mean kinetic energy. Of course, the energy has to be more than the rest energy, right? Energy is the positive number, the kinetic energy plus the rest energy. So, energy has to be more. When I say energy, I mean kinetic energy. If the kinetic energy is more than the rest energy, or of the same order of the rest energy, then the particle is moving with a speed which is close to the speed of light. If the kinetic energy is much smaller than the rest energy, then its speed is rather small. So for a typical alpha particle which comes out, it comes out with an energy. Okay, what units are used here to measure energies of particles which come out from nuclear reactor? Well, actually, mega electron volts would be more relevant. Million electron volts. So, typical energy would be around 5 to 10 mega electron volts. Okay. By the way, that sounds huge, mega being a million. But remember, in the everyday world, that's a tiny energy. An electron volt is 10 to the minus 19 joules. Right? So, in daily scale, that's tiny. But in the scale of tiny particles is actually a huge energy. But typical rest energy of electrons is of the order of half a MeV. That of a proton would be how much? If this is half an MeV, proton is how much? Okay, how much heavier is a proton than an electron? Nearly 2000 times. 1800 is not 1000, it's nearly 2000. Okay, so it's how much? It will multiply this by 1000 and double that. It's around 900, it's more than 900, it's around 1000 MeV. Another name is called a GeV actually, giga electron volt. Alpha particle is 4 times that. So 4000 MeV. So the kinetic energy of the alpha particle, which is of the order of 5 to 10 MeV, is actually way smaller than the rest energy, right? So alpha particles come out with nearly the same speed as daily life objects. Not really daily life objects. They are very fast, but they are much slower than the speed of light. Okay. So, and by the way, by the simple principle of recoil, which is being used here, right? Equal the x was at rest. Alpha came out. Y has to come out in the opposite direction. Y is balancing the momentum. Y is much heavier than the alpha. Say if it's uranium, which is decaying, Y would be radium, right? 234. If it was U238, 238, this is 234. 50 times heavier. So much slower. Okay. So basically, we can actually use non-relativistic relationship between the kinetic energy and the momentum and get away with it. That would be an approximation, but that would be a very decent approximation. Okay. What that means is we can use these results. P alpha, right? This is the relationship between kinetic energy and the momentum for non-relativistic particles. Okay. This cannot be used for really fast-moving particles, but for non-relativistic particles, it is fine. And as we have argued, in a typical alpha decay, the particles do come out non-relativistic. So, this actually tells us, since Py and P alpha are equal in magnitude, they are opposite in direction, but what says here is a square, which is a length square. Here, the numerators are the same. Ty and T alpha, of course, differ because My and alpha differ. And you get Ty by M alpha equals P alpha by My. Right? You divide this by M alpha and this by My, of course, you get the same result. But the reason why I've written this is simply this tells you I don't know. You just add the numerators, add the denominators. Right? You all know this. A by B equals C by D means A plus they both equal to A plus C by B plus D. So T alpha, the kinetic energy of the alpha particle, so this is at least at a decent approximation. This is not exact because we have used a non-relativistic approximation here. But as a decent approximation, this tells us that the alpha particle comes out with the Q, almost all the Q, because My by My plus M alpha is pretty close to 1. And of course, Ty would be M alpha by M alpha plus My. And the two will, of course, add up to Q. So both of them have kinetic energies which add up to Q. Lion's share, or lioness's share actually, the one who actually does all the work, goes to the kinetic energy of the alpha particle. Okay, two important points. The entire rest energy which is available by decreasing in an alpha decay does not go into the alpha particle, but most of it does. But what is even more important, and this is where things become very interesting for particle physics, is that this is a different value, right? Mx, My, M alpha are all fixed quantities. So Q is a fixed quantity. This ratio is a fixed quantity. So that when an alpha particle comes out of a nuclear decay, it typically comes out with a very sharp energy. Okay. Not really the same, it's not true that all alpha particles which come out of, say, radium come out with the same energy, for the simple reason that this calculation was done assuming that the mother particle was at rest. Right? Since the mother particle could move a bit, this calculation would only be incorrect in the frame in which the particle is at rest. Since in your laboratory frame, the mother particle, the uranium nucleus, might be moving, you would typically get some deviation from that. But the velocity of that particle, typically when it's in equilibrium, would be of a few electron volts. That's the kind of kinetic energy the particle would have. That's much smaller than the kind of speed which the alpha particle comes out with. So that difference is there, but it's not a huge difference. So you see alpha particles come out with very, very sharp energies. Okay. So when you plot the number of alpha particles emitted against their energy, you see a graph which looks essentially like this. So this E alpha versus kinetic energy of the alpha particle versus number of such particles, you get a very sharp peak. Okay. Well, actually you may get other peaks. The reason behind that is simply that the decay nucleus may not be in its ground state, may be in an excited state. So the fact that these are also special energies, some specific energies, is a sign that the nuclear energies are also quantized. You only have certain levels, not others. And if that happens, if an alpha particle is emitted with a lower than its peak possible energy, that means the Y nucleus is left at an excited state after that. And what will happen after a while? It will go back to the ground state by emitting a very high energy photon. That would be a gamma. So such decays are always accompanied with gamma emissions. Okay. But the important thing is that energy is precise. Even those other peaks happen at precisely well specified energies. Yeah. This graph is simply, you have a nucleus, say you have a sample which is emitting alpha particles. You have a way of measuring the energy of the alpha particles. There are many ways actually. You just count how many particles you get with what energies. You plot that. You will see that almost all the alpha particles, let's say the simplest scenario. The simplest scenario is all the alpha particles come up with an energy which is peaked very sharply around this value. This value is the value you have calculated here. Why is there this deviation then? The deviation is because the mother particle, the uranium nuclei, might be moving. So that will make some changes, but it will only make small changes. This actually is this broadening of a line. You expect this line to be sharp, that becomes broadened because of the motion of the source. It's called Doppler broadening. For the simple reason that this is basically Doppler effect. Energy shifts because of the fact that your observer is actually not, the source is not at rest with respect to the observer. Anyway, the important point is this. In alpha decay, you get to see very sharp lines. Okay. If you did the same thing for beta decay, yeah. What? Yes, kinetic energy of the alpha particle, number of alpha particles emitted. You typically see a very sharp peak. You sometimes see secondary peaks as well, but that's because of the fact that the daughter nucleus might be in an excited state.
So the kinetic energy versus
number of alpha particles. See, at least number of alpha. That's actually the rate of alpha particles being seen. More precise. Number of particles seen in a particular unit interval of time. We did the same thing with beta. So what happens in beta? X goes to Y plus beta, right? Now there Y is even heavier than beta. Beta is just an electron. So this very small shortfall of energy that alpha actually gets slightly smaller amount of energy. With beta, what should happen is the beta particle should get the entire thing. Okay? Of course the formula would change in the sense that it will be mx minus my minus me into c square. That would be the energy available. That would be the kinetic energy of Y plus an alpha. Y plus an electron now, the beta. And the sharing of energy, with beta it would be difficult to actually use the non-relativistic formula. Remember, beta particles are electrons, the rest energy is only half an MeV. So if a 10 MeV electron comes out of beta decay, or even a 1 MeV electron comes out of beta decay, that's actually already ultra-relativistic. So you should not really be using that formula. You should be using the relativistic formula, something we are going to discuss in the next class, and show how easy it is to calculate that using 4 vectors and the invariants. However, the point is, even the relativistic formula does tell you that you get a very precise single value, just like the non-relativistic formula tells you that. And with beta particles, you should expect this, even sharper. What you actually see is this. Experimentally, this is what you see. Well, if energy and momentum were both conserved, then this would have been impossible. Because if you had a two-body system, a system where the mother nucleus decays into two particles, Y and the electron, and both momentum conservation and energy conservation work, then this kind of a graph would be just impossible. So what are the possibilities? One is energy and momentum is not conserved, which, by the way, was the favored explanation when this was first discovered, for the simple reason that the other possibility was absolutely impossible. The other possibility was, you all know what the other possibility is, by the way, you should know the answer by now. What happens in the beta decay? You have a third particle. Energy conservation and momentum conservation is still valid. It's not just not a two-particle decay. It's a third particle. There's a third particle in the mix, and so now the sharing is not always the same for every particle. Depending on what angle the third particle comes out at, you get different amounts of energy. So basically, Y still carries away very little of the kinetic energy. But whatever the electron doesn't get, that the other particle gets. Okay? But you should realize that at that time, this was a really drastic theory. But at that time, when this beta decay was first discovered, how many elementary particles were known? How many? 3. These are the 3? Well, electron and proton. They did not know that they are fundamental, but still they knew that electrons and protons are there. Neutron had been discovered a lot later. So the universe had only 2 particles. And suddenly you want to change your universe to have a third particle. So this is what physicists do all the time. When experiments don't match theory, you first challenge the experiment, then you challenge the theory, or better you change the universe. So we change the universe. Pauli posited that there has to be another particle there. It took more than 30 years to find that particle because it's so elusive. What? You are not measuring the energy of the neutrino, right? You couldn't at that time. We still can't. Neutrinos interact so little that detecting a single neutrino is a very difficult task. Because we have experimentally found out that this. No, if you could measure, what do you mean? You are measuring the electrons, right? How can you get a picture of neutrino when you are not measuring the neutrino? Okay, the class is over.